Hi, my name is Abdurrahman Ait Ali, and I will be talking about online learning and online convex optimization in particular. This presentation is based on a survey paper or an overview paper done by Shai, Shalev-Shwartz. Here is an outline of the presentation. I will start by introducing what is online learning or online convex optimization in general, and then I will be presenting two different online learning algorithms. One is called consistent and the other one is called halving, and I will be showing the logarithmic mistake bound of the halving algorithm. I will later on talk about two convexification techniques. One is called randomization and the other one is called surrogate loss function. Finally, I will be talking about online gradient descent method, and I will be showing a demo of the perceptron implementation as an example and show the regret bound or the bound of the number of errors. So let's get started. Okay, what is online learning? Online learning is the problem that in which we try to find the best predictor based on a sequential flow of data. So we have a prediction model and we have a sequential flow of input data that allows us to improve the prediction model at each round. So we denote round as t, and then the input data at round t as xt, and then the prediction of our prediction model as pt, and the feedback or the correct prediction as yt. So the feedback can have different forms or types. Why this is important? Online learning has many applications. Some of them are practical, some others are theoretical. Practical applications are spanning different fields, but generally speaking, artificial intelligence, machine learning applications, etc. Theoretical applications or theoretical interesting points are the study of the limits or the performances of the algorithms. In particular, we will be talking about regret or the bound of number of errors of the algorithms. So let's give a small example or a very basic example of an online learning problem. Here I'll be presenting prediction with expert advice, a very basic online learning problem. So at each round T we have the experts, and the input data we get is the advice from all the experts, and this is denoted as xt. And then we pick one prediction, pt, which is basically one of the d experts, and then we receive a vector of costs, yt, which corresponds basically to the costs of following the advice of the experts. And then the loss of our prediction or the loss of the learner is essentially the loss or the cost of choosing that expert. LPTYT is YT of PT. A very simple example of the hypothesis space is constant predictors. Constant predictors are basically all the hypotheses in which we choose the same advice or expert advice. This is just an example of a hypothesis space. Okay, one way to measure the the performances of an algorithm, an online learning algorithm, is the concept of regret. Regret of a hypothesis H star is essentially the sum over all the rounds of the difference between the loss function value of the prediction minus the loss function value of the prediction of the hypothesis using the hypothesis. So it essentially quantifies the number of mistakes that are done by the algorithm. And this depends on the choice of the loss function L. Alternatively, we can actually span or extend the concept of regret to the set of hypotheses, or the hypothesis space, or the hypothesis class, by taking the maximum of regret of hypothesis. So the maximal value of regret of hypothesis is essentially the regret of the hypothesis class. A simple example of a learning algorithm is a consistent algorithm. The basic idea is that we have a kind of a dynamic set of hypotheses that we reduce at each round. So at round t, for example, we receive an input data xt, and we choose randomly one of the hypotheses that is in the set of in our dynamic set of hypotheses, and then we predict using the hypothesis, and then we received the correct prediction. What we do here is essentially to remove from our set of current hypotheses all the hypotheses that are not consistent with the previous uh, with the current prediction. So that's it for the consistent algorithm. The halving algorithm. The halving algorithm is another online learning algorithm. It improves the consistent algorithm in a sense that at each round we get an input data, and we want to we do a prediction such that we take the prediction that is the most predicted in using our set of feasible hypotheses, and then we receive a prediction, and what we do is we update, just like how we did it in the consistent algorithm. We update our set of feasible hypotheses. But here, when the prediction is wrong, we take at least half of the hypothesis set. We take it out of our hypothesis set. So we remove at least half of the hypothesis when we have a wrong prediction. The mistake bound. It is easy to see that in the consistent algorithm we have a maximum number of mistakes, which is the size of the size of our hypothesis test minus 1. And however, in the halving algorithm, it's logarithmic. It's logarithm of the size of the hypothesis space. The logarithm comes from the fact that we halve at each round, we halve the size of of our hypothesis space when we do a wrong prediction. That's essentially what the proof says. Online convex optimization is a particular case of online learning in general. Why? Because the convex terms, the convex term comes from the fact that we have a loss function that is convex and a set of feasible predictions that is also convex. So in general, we have here an online convex optimization problem. There are two ways of doing convexification. One of them is randomization, but before explaining randomization, I'll be introducing the covers impossibility result, which is essentially that we cannot find a learning or build a learning algorithm that is that has a low regret, which means that the number of errors or the regret uh, is less is bounded by a sublinear term in terms of number of rounds. Even if we take a small example where we have only two hypotheses. So to solve this impossibility result, we use realizability. But realizability is a very strong assumption, so what we do is use randomization. So randomization changes the structure of our problem using probabilities and randomization in order to build a prediction space that is convex, as we see here. This is the space of probabilities, and we build also a loss function as an expected cost function using the probabilities um, in order to build or to construct a convex loss function. So this is one way to do convexification. Another way to do convexification is using surrogate loss function. The idea here is to bound an original non-convex loss function, to bound it to construct an upper bound. There is a loss function that is convex. So there is a procedure to do this. We basically reparameterize the problem. We include different parameters. In a sense, it can also be a randomization, but what we do is we construct a loss function. There is an upper bound of our loss function, and our loss function is non-convex. So what we do is we construct a loss function that is convex, and that is an upper bound of our original loss function. An example of convexification using surrogate loss function is, for example, here for 0-1 classification problem. What we do is we basically reparameterize the problem from instead of using directly PT and then the loss function as the absolute value of PT minus the correct prediction YT, which this original loss function is not convex. So what we do is we change to an upper bound function, loss function, that is convex, and thus we get a convex problem. Two ways to solve online convex optimization problems. One is called follow the leader, and the other one is called follow the regularized leader. I will explain what's the difference between the two. First of all, follow the leader, it is actually in a way it can be seen just like the consistent algorithm. What we do is we choose the prediction that has the least loss function value for the next round. So for the next round, we choose the prediction that minimizes uh, the total loss function value. However, this follow the leader method is actually it fails basically when the method is unstable. For instance, when the W's between each round are varying, or the variation of W is quite high. So that's why what we do is, to solve this, we do add a term that is a regularization term, and then we end up with follow the regularized leader method or approach. If we apply this approach to a particular convex optimization problem, which is online linear optimization in which the loss function is not just convex but also linear. If we apply it with a regularizing term Rw equal to 1 divided by 2 theta norm of W square, we end up with an updating scheme like this: Wt plus 1 equal Wt minus eta Zt. This looks like a subgradient or a gradient descent method, and we call it online gradient descent. Subgradients, as we all know, can be represented as follow. Here, for example, we have a convex function, again here a convex function, but here we have one single subgradient, here we have different subgradients, and those are the inequalities that a convex function satisfies, and subgradient is noted as this. The gradient is noted like this, delta FW, and subgradient is also noted like this. So online gradient descent algorithm, it essentially uses a parameter eta and the subgradient to update the prediction. So the updating rule is essentially a gradient descent method. And this allows us, the fact that f is convex allows us to do some kind of regret analysis using the linear expressions. Here is an overview of the steps to perform a regret analysis. The objective is to get a regret bound in terms of t. We start using the convexity property of f, which is ft, which is the loss function, and then we use the Lipschitz property of the subgradient in order to derive an expression in terms of t, and the objective once again is to get a low regret algorithm, which means that the bound should be sublinear in t. Here is an application or an example of the bounds. For example, follow the leader. We use the inequality from the convexity property of the loss function. Same goes for the regularized leader. However, in the regularized leader, we have a customizable parameter, which is the regularization function, which allows us to manipulate the upper bound. For example, if you use a regularizing function Rw equal 1 divided by 2 theta W, the norm of W square, we get an upper bound in terms of the subgradient, and that upper bound in terms of subgradient can be used to derive the regret of online gradient descent algorithm, and for particular values of different parameters, one can show that the upper bound of the regret of the algorithm is sublinear in terms of t, which is what we want. A small example of online gradient descent implementation is the perceptron. So using it on binary classification algorithm, or we essentially have a mistake, a loss function, 0-1 loss function, which is defined like this. However, this is not convex, so what we do is we use surrogate convex loss function, in particular Henge loss function. We get a loss function that is convex, and then we get a convex optimization problem. Once the convexification is done, we use online gradient descent algorithm, and then we build our learning algorithm using the online gradient descent method. So if the prediction is wrong, we have this prediction update scheme. Otherwise, we keep the same prediction. This is essentially because we used the subgradient update scheme, and our loss function that we choose has a gradient equal 0 if the prediction is correct, as in here, and if the prediction is incorrect, as in here, the subgradient is minus ytxt, and we have chosen eta as a positive parameter. We've chosen it to be equal to 1. And we can show that the bound of number of mistakes is r divided by gamma all squared, where r is the maximum of the norm of all the input points, and gamma is minimum distance from W star, which is our realizable hypothesis. So here we show the demo. Hopefully it's working. I hope that this is working. Yeah, sorry. Yeah, okay. So this is a demo. This is an implementation of perceptron using online gradient descent for the following parameters: r equals square root of 2 and gamma is 0.1, and we can see here that the number of errors is actually bounded, and this is the number, the x-axis is corresponding basically to the number of rounds. So that's it for the demo. And so we covered basically what is online learning algorithms, online convex optimization in particular. We presented halving algorithm and its logarithmic mistake bound, and also some convexification techniques, randomization and surrogate loss function. And we have seen a demo on the perceptron using online gradient descent method, and we showed in theory and also in practice we checked in practice that the number of errors is bounded, and the regret bound is satisfied in practice as well. So thank you very much, and that's it. Bye.